Okay. So today we're going to talk about parabolas. So let me see.
I'm just talking about something a little stupid, it's not just something. And then she practice with them. It's a really short, they like to put it in there. They gotta do so. It's, probably the first thing is,
Okay, so parabolas, they are kind of like in terms of difficulty, what comes after lines. So let me just remind you, like the equations of lines, because it's like a useful comparison to have. Before we have seen equations for lines. So the standard way in which I was writing the equation of a line was something like y equals mx plus b, right? So here m represents the slope and b represents the intersection with the y-axis. So let me just draw a few examples of how this looks like. Just to remind you how how these lines work. So for example, if you have something like this, if you had a line of this form, like the line is what you would call increasing, so the slope had to be positive in this case, and the intersection with the y-axis is precisely what B represents. So this is kind of like the point here of comma B. So this is more or less how a line with positive slope looks like. If the slope was negative, like then maybe the line looks like this. So here the slope is negative, and now the intercept would be somewhere here. When so that's positive slope, negative slope, slope zero just means that the line is completely horizontal. So slope zero would be like this. And then you could also have like a vertical line. Would be the only one that doesn't really fall into this format, but like a vertical line looks something like this, where like f just takes, so it's like the same value. Okay, so when it comes to lines, this is more or less all the possibilities that you had: positive slope, negative slope, zero slope, and then extreme case where there's not really like a slope, where it's just like a vertical line. So here you would say that there's no slope. Okay. Now, this is for lines, right? So the point about a line from our perspective, like from the algebra, is that x is just multiplied by a constant, but there are no higher powers of x. So there's nothing like an x squared or an x cubed or x to the 4. So in terms of difficulty, what follows after lines is what's called quadratic equations or parabolas, which we have been working with them a little bit up to now, but now we're kind of going to think about more in terms of the lines. So the next thing is like parabolas. And the equation of a parabola, the usual way to write it is something like ax squared plus bx, kind of like size and numbers. So that is how a parabola is typically written. So here are some examples of things that would be parabolas for us. Like, you could have like y equals x squared. That's actually the one that I'll start with today. Y equals 2x squared minus x plus 3. That's a little bit more complicated, but it kind of still follows into this category. Minus x squared plus 5 is another parabola. This is another parabola. So it's basically like the only requirement for this to be called a parabola is that the number in front of x squared is not 0, so that you have really something that starts with x squared. But the number can be 1, could be 2, could be negative, like there's not be another thing like this. So a is just any non-zero number. So a is any non-zero number. And B and C can literally be anything. They could be positive, they could be negative, they could be zero. We don't care about what they are like in terms of like recognized qualities and parabolas. So B and C can be positive, negative, or zero. So it can be any number. So today, like basically what I was going to kind of discuss is just like how to draw these graphs, like the graph for like the specific cases, depending on the signs of A, B, well, mostly the sign of A, that the most important for the parabola, as you'll see, and then like some other conditions that can follow also from B and C. So what is the effect of all these numbers like on the shape of the parabola? Yeah, for to discuss. So let me start just with like the most simple parabola possible, which from there we can kind of build up to some more complicated cases. So here's the simplest case, which is just something like y equals x squared, which I'm pretty sure we have drawn before on the board. So how can you draw y equals x squared? Like basically you can do a table here. Start with the table always if you like. So 0 goes to 0 squared, which is 0. 1 corresponds to 1 squared, which is 1. -1 corresponds to -1 squared, which is 1. 2 corresponds to 2 squared, and that's 4. -2 goes to -2 squared, which is also 4. So what you start getting is like something like this. So I have so what I'm saying is that zero goes with zero, so you get something like you get that point. 1 corresponds to 1. -1 also corresponds to the point which is the value 1. So it goes like that. Then 2 goes to 4, like this, and -2 goes to also 4. So you start joining with dots, like if you did this like for a lot of dots, for a lot of values of x, and you just join all the dots together, the graph, which is how we call this, the graph looks like this. Something like making sense. Um, And so then, like the first thing you can kind of like look into is like what happens if you just multiply this by a number, like I put like a number in front of x bar, which is not necessarily 1. So let's just like the first level, like increasing the difficulty a little bit would be something like let's do, and I'll then show you what happens in general. So let's do something like y equals 2x squared. Okay. So like what you can do in this case is use the table just to see how this looks. And I'll just put like the same values for like this table. I'll just put 1, 0, 1, -1, 2, -2. So what happens with x? With x equals 0, you get 2 times 0 squared, which is still 0, because just that like 2 times 0 is 0. Then here you get 2 times 1 squared, which is 2 times 1, which is 2. Then you get 2 times -1 squared, which is still 2 times 1, which is 2. Okay. Then you get 2 times 2 squared, which is 2 times 4, which is 8. And then you get 2 times -2 squared, which is 2 times 4, which is also 8. Okay. Okay, no, I found this value. So like, it's kind of convenient actually I could draw again the XY plane and draw it separately, but it's actually convenient to draw it on the same picture to compare it with the kind of like the reference parabola. So like 0 matches with 0, just as in this case, then X matches with 2. So X equals 1 matches with 2, so X equals 1 here, so and 2 is here. Okay. X equals -1 matches with 2. So here's -1, so here's 2. Okay. Then 2 goes with 8. So here was 2, 8. I don't even have it on the scale, right? So I have to kind of put like the 8 really high up here, right? Like I actually had to extend this. So 5, 6, 7, 8. So 8 is there. And then -2 also goes with 8. So that is how the graph of y equals 2x squared looks. At this point, it's kind of convenient to just kind of like do like the analysis a little bit more generally, doing like a bit of an animation. So, what does this look like? So my reference parabola, I'll leave it as y equals x squared. So like usual to have as a reference. So I'll put like the same colors as the definition. Times y equals x squared. And then I'll put like these other parabolas is a times x squared. So for example, let me put this in green. Okay, so this is, for example, 2x, y equals 2 times x squared, which is the one that I just drew also on the board. So now what I'm going to increase is just this number in front of x squared so that you can see the effect of what happened there. Okay. So if you start increasing the value for a, which is the number in front of x squared, what do you see occurring? Like this graph, which is called the parabola, gets closer and closer to the 100, right? If that makes any sense. So as you start increasing the value for a, you know, kind of like you're making it move further and further to the y-axis, and if you kind of actually go opposite of that, if you start decreasing the value for a, like it moves further and further away from the y-axis, right? And like actually once like a is between 0 and 1 is like now very, very close to the x-axis. Okay, so the higher a is, the bigger a, the closer the graph is to the y-axis, if that makes sense. And what will happen, then what happened if use negative values for A is that you turn it upside down. So for example, y equals minus x squared is just like the one that you had before, but reverse. So like, it points downwards and then like the same behavior kind of starts happening again, but with negative values. Okay. So when the number gets really, really negative, like it gets closer to the y-axis, and when it's between -1 and 0, then it's closer to the x-axis. Okay. So basically, A controls what you refer to as the concavity of the parabola. So let me just write that down. So what is occurring is that when you have something like um, this A, this number A is related to the concavity of the parabola. So when A is positive, like the parabola looks like this. So this is how the parabolas look like more or less for positive A. So here A is positive. And this is called like a concave up parabola. So this parabola is called concave up. So one way to memorize the name is that you kind of think about it like the graph as a sort of like face. So it's like a smiley face. So if it's a smiley face, you're happy, so your mood is up, So like that's one way to think about it. So and when A is negative, when A is negative, when A is negative, is here A is negative. And it points down, like so that's why it's called like a concave down parabola. So it's called concave down parabola. And again, if you think about it in terms of a face, it's kind of like a sad face, so it kind of matches also like how you would refer to it in terms of like mood or a sad face. So the number in front of x squared basically just tells you whether like it's a happy face or a sad face, basically. Like that's like the only effect or the only consequence of that number. The bigger this number gets, kind of like the more you kind of squish the face into the y-axis. But I mean, but qualitatively, you just care whether it's happy or sad. That only depends on the sign. Like how much is like getting close to the y-axis or the x-axis. That's like that does depend on the specific value of A. But whether like the mood of the graph only depends on whether it's positive or negative. Okay, so that is more. This is what happens when with the number in front of x squared. So the next step is to see what happens if you have this plus bx. So as I told you, the parabola, the more general parabola is No, like the general case of a parabola is something like a x squared plus bx plus c. So like I already explained what this part refers to, and now I have to tell you what happens if you have like a term like b times x. Okay, so for that, let me just do again like a specific example, and then I'll show you what happens in general. So. Let's say you have something like y equals x squared plus b times x. Okay. And b is just like some non-zero number. So we can even think of it being positive. So here b is positive, let's say. B. But that's not really necessary, but just to kind of start with something else. Okay, so I want to understand how this parabola looks like now. And to do that, that is precisely why I was kind of very annoying yesterday about completing the squares. It is very easy to understand how this looks like if you remember the completing the squares formula. It's like almost immediate. So if like this x squared plus bx is exactly the same thing that I was writing over and over and over and over yesterday. So if you use like completing the squares formula, well, what the formula said is that instead of writing this in that way, you can write it as let's see, x plus b over 2 squared minus b over 2 squared. Okay, so that is what completing the squares formula allows you to rewrite this as. So instead of trying to understand the graph this way with the formula written this way, I can just think about it in this way. So I'll just think about the parabola in this way. So think of the parabola as which again, this is the same thing as like x squared plus bx, but it's like a more convenient way to write it for now. Okay, so I'll understand this graph into steps. Like first step, let's just figure out what y equals x plus b over 2 squared looks like. So let's start with that. Step one. What is y equals x plus b over 2 squared? How does that look like? Okay, so maybe hopefully this rings a bell, but what I'm doing here is like adding b over 2 to the variable x, right? So that is similar. Do you remember when we did this like a couple of days ago? When I said, well, let's say you have like the graph of a function in terms of x, and then you do like something like f of x minus 1 or f of x plus 1. What happens with the graph in this case? Anyone remembers what?
We're kind of like if it was f of x minus 1, it would be instead of moving forward to the right on x by 1, it actually was to the right.
Correct, good. Excellent. So if it's with a minus, it moves to the right. And if it's with a plus, it moves to the left. So basically what you're doing here is that you're taking the graph of x squared and shifting it to the left because it has a plus. Okay, so this is like, it's a shift to the left. Of y equals x squared. Okay, so basically, let me do a couple of pictures here. So what I'm saying is that you could like you have something like the graph. I think I used it in blue. It was a graph of y equals x squared, and then you shift it to the left by one amount b over 2. So let's just take all this graph. So there's like a distance b over two here. Okay. But like it's to the left, so I'll just put it like as a point, it would be like negative b over gamma zero because because we move to the left. So now this is the graph of y equals x plus b over two squared. So it looks exactly like this as the original graph, but all of it was translated to the left. So far so good, is that making sense? And then, so the parabola is not just this part, it's also this part. So I also have to subtract this part to the graph. So like the full equation is not just this term, it's also this one. So let's step two, let's just consider. Let's just consider what happens with that. Well, so now what you're just doing is subtracting from the graph like a number. And I don't know if you remember, we talked also about that. I told you about that, what happens if you have a function and you add a number to it? It just moves it up or down depending on what the number is. So in this case, since it's like a subtraction, it kind of brings all the graph down by at this amount. So essentially, what the graph of this is going to look like, it's kind of like imagine taking the orange graph and then you just shift it down by what amount? B over two squared. So this would be. And that is how the graph would looks like in this case. But so essentially what like based on the what's kind of important to understand is that like if this doesn't really change the fact that like if you think about it in terms like oh is the parabola up or down like happy or sad, it still always continues to have like the same like shape. So the shape doesn't change when you have the bx. The only thing that like changes with the bx is where like the parabola kind of hits the bottom. So the bottom of the parabola before originally was at the origin, right? The minimum, which is what you would call the minimum. And then like the b just has the effect of like moving the minimum to some other place, basically. Let me, is that making sense? Let me show you how that looks like on the computer, just because it's kind of like fun to keep track of that. I'll kind of like do like a summary in a second of like all the main properties, but I'm just kind of showing you how you think about it. So. So. Okay, so essentially what I'm going to do, I'm sorry. So I have the original parabola, which is y equals x squared, and I'm going to plot for you y equals x squared plus bx. Okay. So the green one is like the one that has been shifted. So for if you just add one to it, you see like you kind of it's not super clear the effect, but that's because I have to add like a bigger number. So if I start like increase the number here. You see, as you make the number in front of x larger, you're kind of like shifting the parabola up and left. Which is what's going on. but it always still has like the same shape. It's literally just like some sort of like translation of a parabola. You just grab the original parabola and you just move it down. Okay, and that's what happens if you do like a positive, use a positive coefficient in front of x. If you use a negative coefficient in front of x, essentially it's the same but in the opposite direction. So like the translation is kind of to the right. Let's say this. Okay. Like then it's up, like left, right, depending on whether the coefficients are positive or negative. The important thing is like again, like the qualitative feature in the sense like, oh, they're both happy is preserved. So like the only effect of doing this is to shift where the parabola like reaches like the bottom, like the bottom of the parabola, which is like this point, which is called the vertex. I'll kind of write it in a moment. And if you had done this with a coefficient of a that's negative, like minus x squared. So y equals minus x squared, and then for here, it is exactly the same idea. It's a shift, but it's kind of reversed. So it still moves to the left or to the right, but also now like in the first two quadrants. So like it's now like more like at a higher level. But like the important thing is that if this is if like the original was concave down, like the new one is still concave down, so it's still that side. Okay, so then we have that down. I'll kind of draw it a bit more like. So what I'm saying is that, so what is like what happens in general, so in general. In general, if you have like a parabola which is y equals a x squared. Here is a has to be positive for it to be happy. So here a is positive. When you have something like y equals a x squared plus bx. Oops, let me put it here. So this is how the parabola looks like when both a and b are positive. So here's like a positive, b positive. So here's b positive. Because with b positive, it's just like a translation to the left, and this point ends up being like minus b over 2a. And then what is the other value? Oh yeah, minus b squared over 4a. Okay, and if the b had happened to be negative, like then the shift is to the right. So and is this still the minimum is still that it has the same coordinates. Okay, and then so like what I'm saying is that when the parabola was concave up, when it's happy, like like the plus bx just moves it down to the left or down to the right, depending on whether b is positive or negative. Okay, and then let's see. if the parabola had been like concave down. And then we have different colors, yes. So here A is negative, so this is concave down parabola. Then this is y equals ax squared plus bx with b still positive. Okay, I'll try not to erase this picture because it's important. And then this is and then the other one is when you like when it's this is with B. I mean, I have some of these pictures in the notes, but I'll add kind of all the cases on the notes so that you can have them there. So the important thing to observe again is that like the plus bx doesn't change the shape of the parabola. It's still like minus or side. It's just like where it's like located. So the minimum, this vertex is on this. This is what you would call the vertex of the parabola, the vertex. So it just basically changes like where the vertex is. So in these cases, it's like a mean, and in these cases, it's like a max because that's the highest point of the graph. We'll use that on Monday. Today I kind of just will give you a few examples for you to try to graph. On Monday, I will use this stuff like to some like applied problems about parabolas and how to I mean, there are many problems like applied problems where like the equation ends up being like a parabola, and from there you can find the mean or the max of by locating the vertex of the parabola. It's kind of like useful. But I'll do some examples of that in uh, like after a Monday because I like it does so far to questions about this. Okay, last piece of information, which is the easier one, so that's why I focus more on this, is if you remember again, like the equation of a parabola is ax squared plus bx plus c. So a is whether you're happy or sad, that's what we just discussed. B just changes like where the mean or max of the parabola occurs, like the top or the bottom of the parabola. And C, so we still haven't talked about C, so let me just focus on that. That actually is like not not too different from what we just did. So the only thing that happens is that like when you add plus C, it just shifts up or down vertically. Exactly. So like that's the easiest one to understand, which is why I didn't focus too much on this. So what this will do is just like once you understand this graph, you just move the graph by an amount C vertically. It just moves the graph of vertically by an amount C. Okay. So I'll just kind of do it with one of these because otherwise like, it will take a little bit too much time. I must say. So for example, let me just do it. Let me do it with these ones. So for example, because it's really the same in everything. Okay, so like let's say here was y equals ax squared plus bx. Right, we had already discussed this. Okay, So if you just add plus c to to this equation, you just move everything up by that amount. So like just think about there like being like a distance, a vertical distance of c between these 2 points. And so this is how the graph of ax squared plus bx plus c would look like. So you just do like an upward shift of the graph if c happens to be positive. If c is negative, then you just bring the graph even more down. So this is like for c positive. Okay, so this point is still, it has this minimum, in this case has this still the same coordinate for x, but like the y coordinate just moves by an amount. And yeah, like the other one, again, like the other, like all the other cases are exactly the same, like if it's plus c to this one, just move it up. If it's, and if c is negative, it moves it down and these. So like the plus c is like, so essentially, basically what I'm trying to say is that to graph a parabola, what you can do is graph first, the stuff without c, and then you just do a translation. You can graph first. So this is really the important stuff, and then the plus C just moves it up or down, and then. Oh, yeah, sorry.
So like to put this all together, basically, so A, like starting off the graph, A positive is just smiley face, like it depends on whether
Correct.
it's smiley face or smiley face, and then B is, it shifts the graph either left or right depending on if it's plus or minus B,
Yes,
and then C is moving the graph vertically by the amount of C.
yeah, let me do it for one, like the things I kind of want to erase too much, but let me put it, I'll put it here, like I have some room, like on this spot. So let's do it, for example, for, let's say if I wanted something like this graph, 2x² plus 4x plus 3. So the first thing I notice is that a, okay, so I read off a first, okay? So a is still, in this case, is 2. I don't care about the fact that it's 2, I just care about that it's positive. Positive means that it's going to be concave up, so it's smiley, okay? So this is positive. So it's going to be a concave up or happy parabola, so concave up. I actually like to put like some sort of eyes to the parabola because it makes it easier to remember, like in terms of like an emoji, it's like a happy emoji. So that actually that works a lot, like if you ever have to take calculus, because there's a thing called second derivative test, which is what tells you if a function has a max or a mean. And essentially what happens is that you look at a parabola and the concavity of the parabola is what determines if you get like a max or a mean. So really like the parabola is like a very important thing because it is what determines a lot of stuff that occurs in calculus. So like the parabola is really like important, like it is like serious business. Like it's actually one of the important things like to understand well because it appears everywhere. So but okay, so I know that it's going to be a happy face, right? And the B in this case is 4. So this is going to be positive, right? And because it's positive, positive is here, right? So it's going to be moving to the left. So I'm going to shift the graph to the left because it's the positive case. So this is a left shift. So, and again, as I said, I will just focus first on the first terms. Yeah, sorry.
So with the B, if it's kind of the same thing where like, if it's positive, then it's opposite day, so I guess
Right,
go
yeah.
down left and get down, even though.
Right, it also happen, in this case, it happens to be down, but okay, the reason why it happened to be down, actually, let me explain it again, because when you completed the squares, right? If you think about it from completing the squares. Okay, this is the part that moves its left, right? But there was this extra piece that is the one that moves it down, so that is why it's left down, like, if it were only this, right? It would only move left, but like the full equation is with minus this term, and that's what brings also down the parabola, if that makes sense. So, yeah, like, what I'm trying to say is that, you know, that's why I kind of drew the stuff in two steps. Because if you were just to graph this, like it's just moving it left, but like the equation actually has like this extra piece that brings it down as well.
Without the C.
Even without the C, exactly. Because this is like x squared plus bx, right? That's what the completing the square formula said. So that is why, so like from completing, like that's why completing the squares was so important, because from the completing the square formula, you kind of see, oh, there is like a left motion together with the downwards motion, you see.
And when it's upside down, it's the same thing, but like
Right,
if you flip
correct.
it's around.
It just changes like the smiley face, yeah, but it's still, if it's like the concavity, if it's negative, it's still, kind of works the same, it's just that. Like the thing is that, you do get like an A in the denominator, so when A happens to be negative, minus minus becomes plus, and that's why it goes up.
Okay.
Yeah,
Thank you.
yeah, sure, thanks for asking. So. Yeah, I'll give you a few, for you to try like in a second after the quiz. But so I'm just saying, like, okay, I have to draw a happy face, move left and down, right, as in there. So it kind of will look like that, it's just that, so like this point is going to be minus b over 2a, comma, minus b squared over 4a. So minus b, like that b is 4, so it's minus 4. 2 times a is 3 times 2, comma. B squared is minus 16 over 4 times a, 4 times a is 4 times 2. So this gives you negative 4 over 4, and then negative 16 over 8, which is negative 1 comma negative 2. So what I'm trying to say is that the bottom of this parabola is at the point negative 1 comma negative 2. So here's the negative 2, and here's the negative 1. Okay, that is how that parabola looks without the C. Now I have to add the C. So this is like, sorry, let me just write it like the equation. So I'm plotting for you 2x squared plus 4x. Okay, if I want the plus C, I just move everything up by 3 units. So when I add 3 units to this, like I'm already on negative 2 here. So I'll use 2 units to get to 0, and then I get another unit here. So I'll put it like there's a 1. And this is like the full graph that I want. I should have this like the same color. You see, so like the distance between these 2 points is of 3, because it's like 1 to negative 2. So 1 minus 2 becomes 3. So that is you would like draw it. But it's always kind of like you ignore this piece for the moment, for the time being, like graph it without that piece, and then you just move it up or down. Yeah.
Technically, if we, let's say, forget exactly where to move it, then we could just plug it in.
Yeah, you actually, right.
Formula, and then we get.
Yeah, if you plug it in, you kind of like also would get where it should be. Yes, correct.
Gotcha.
Yeah. So yeah, you can kind of like plug it in to kind of like see what the y value would be, and that tells you whether it was had to be positive or negative or left or right and other things. But I'll leave this on the board for you to kind of refer to it like once I give you the problems. Is that okay? Okay, so like that is what it was important, like what I wanted to say about graphing. But hopefully it kind of gives you like a sense of why, like yesterday I was like, oh, this completing the square stuff is useful, because really without that, you kind of get stuck quickly if you want to understand how the graphs of the parabolas look like. But once you have the completing the square technique, it's pretty easy to see that, and the shift to the left or right, up or down is like what we had also studied before when we were talking about functions. So it's kind of like a nice combination of a few topics that we have already taught. Yes, sir.
So you kind of lost me after finding the point -1, -2.
Oh, here,
So I'm aware that it goes up, right? But,
Right.
Are we gonna be at any point to ask, find any other points on that?
so usually for parabolas, like the only important point that you really care about, is like the what I'm calling the vertex. So really like, in this case, like because it's concave up is a mean, right? Like the bottom of the parabola. If it had been concave down, it's like more like a max. So typically for parabolas, no, you would only be asked to find the vertex, because once you have the vertex, you can kind of like draw the rest of it, once I know that this is like the bottom, like, once I know this is the vertex, then you just draw like either a happy or a smiley face, depending on whether it's concave up or down. So kind of it decides like in the entirety of the, like rest of the graph, if that makes sense. And for the applied problems that I'll do on Monday, it actually knowing that like is mostly what you care about, because that's I don't want to kind of like get ahead of time. So like it will, for those applied problems, I will do like word problems, like knowing the vertex is essentially what you're after. Because it will be kind of like, like just to give you like a heads up of what we want to do. It's like, oh, you want to be, you want to like fence a terrain, like say it's like a rectangular terrain. So you have like, imagine just have like a certain amount of fencing material, but you want the terrain to, like, it has to be a rectangle, but you want the terrain to have the maximum amount of area possible. And that is the keyword. You want the maximum amount of area possible, and then what you'll see is that you can kind of set it up as in terms of a parabola, and the vertex will tell you the amount of area you can put inside the terrain. So like, I'm kind of like not saying it too well, because like there are a few details that we'll have to see, but really like the vertex is more or less like the only point of the parabola that you care about. Because like, once you have it, like you can kind of graph the rest of it, and then, and for applied problems, that's usually also what you want to find. So for example, like there are these problems like in physics, like, when you throw like a rock or something like that in the air, and that is described by a parabola equation. So like the analog of that is asking, oh, what is the maximum height that the rock reaches? And that is like the vertex of the parabola or things like that. That would be one of the applied problems that I'll give you like on Monday to work on. But like, so mostly, you care about the vertex. And sometimes like also like, okay, like the other case would be maybe when the parabola kind of like for example here, like if you were to extend these graphs, it would cross the x-axis at some point, and that can also be useful. But when, and again, I'll kind of say that on Monday, but when it crosses the x-axis, that's when y equals 0. So you kind of just take the equation of the parabola, set it equal to 0. And that's why, like, before we were like solving equations, ax squared plus bx plus a equals 0. But so besides those two things, there's no other points in the parabola that you really care about too much. Okay, good. So yeah, so as I said, this is what I wanted to tell you for today. So let me pause here.